Hey, good morning, everyone. Even though the numbers are a bit lacking, let's start the class. There's no point waiting too much, and about half a group is already here, I guess. So, yes, yesterday we had the second contest. So let's do the same survey. Who thinks it was too easy? Okay, happy to hear that. Who thinks it was okay in difficulty? Great. And who thinks it was too hard? Okay, I hope the others are not staying away because they thought it's too hard, so there's no point attending anymore. But anyway, so to be fair, I myself haven't checked that many Latin American continental championships because the availability of those contests online is not the best, I guess. But based on the few contests I've seen, and also based on the difficulty we have at the European Championship, so this was close to something that you can expect at the Latin American Championship, I guess. Maybe replace one problem with an extremely difficult that nobody can solve. But the difficulty I think here is close to continental championship. So good job, everyone. And let's discuss some solutions. Okay, so there is a task that was solved by a relatively lot of teams, so because of that it might not worth explaining, but I checked a few solutions and it might worth sharing a few thoughts. So let's talk just a little bit about the task lumberjacks, I think it was lumberjacks. I have the example from the statement. Okay, so there were some points over a circle, and each of them had some strength, which represents how much time do we need to cut that branch down. And for example, these values were 2, 3, 4, 1, 7, and 10. In the example, okay, and on the previous branch there is a lumberjack who is cutting down the next branch. And if he's allowed to cut it for this amount of time, then the branch will fall together with that lumberjack, so he won't be able to continue cutting down the next one. Okay, and of course this is not too difficult, but we also had updates. An update can change the strength of a branch, which means it might take more or less amount of time to cut down after an update. Okay. So yeah, first it seems confusing because the distribution of which lumberjacks are falling and which lumberjacks won't can follow some strange patterns. But there is one specific type of branch which is interesting for us. There is a set of branch that will fall regardless of what is going on at faraway branches. And the branches I'm talking about, the special branches, are the ones where the amount of time it takes to cut it down is at most as much as the value for the previous one. The special ones are the ones where this value value I, was the amount of time required to cut it down. So if it is lesser or equal than the amount of time to cut down the previous one, it's usually I-1, but sometimes you go around the circle. So yeah, so it just denotes the previous one. Okay, so I claim that if this holds for a branch, then that branch will be cut down regardless of what is going on. Okay, and the reason for that, let's consider this one. This branch takes 1 second to cut. So if the previous branch takes at least 1 second to cut, then there is no way this lumberjack will fall down before this one. So he is guaranteed to fall down no matter what is going on over at other nodes. And if you check it, then this is the other special node in our case. Okay, so we have these two special nodes with this property, and after that I claim that these must fall no matter what is going on. And I claim that for every other non-special node, they will fall down in like an alternating way. So one falls, one stays, one falls, one stays. Others fall down, alternating. And this is actually pretty easy to prove if you start from a special node and think about what is going on. So, so if this is guaranteed to fall down and this is not special, then he will stay because that property doesn't hold. But if he is guaranteed to stay, then no matter what is the number here, this will be cut down eventually because he has an infinite amount of time to work, right? So it must fall down, but this is not special. Okay, and the same repeats. So if a node is not special, so the converse holds, then the next one cannot fall. And if somebody won't fall, the next one must fall. So that's why we get this alternating pattern, right? Okay, so this was essentially the critical observation to find a relatively simple implementation or simple solution to this task. Because after that, if you consider an update, then it turns out that even with updates, it is enough to maintain the set of special nodes. If you know which nodes are special, then by the alternating property, you can like very easily figure out you have to take care of several like plus ones or minus ones. Because there might be special nodes like next to each other as well. But maintaining the set of special nodes, you can easily get the number of I don't know what was asked by the task, but you can get either the number of guys who are falling and the number of guys who are staying up, right? So let's just maintain the set of special nodes. Okay, and actually this already spoils what I'm going to do. I'm going to maintain it in a set. Because actually when you are doing an update, you can immediately see, because of the definition of a special node, that if you change some value, then only this node and the next node can become special or become not special. So only two nodes can change states. Okay, either the one who is updated or the next one, because for the next one, the special property depends on the value of the previous one, right? So for an update, only, or at most two nodes may change state. So it is easy to maintain in a set, because you just have to find the two nodes that might change state, determine whether they change state, and then you are done. Okay, if you want an easy implementation, you can always just remove the two adjacent points, no matter what's going on, and you can add them again if required. So there's like a very easy way to implement it using a set. Okay, finding these things might affect a competition, a contest very much, because if you do a very tricky implementation of something, there's a good chance that you will accumulate a lot of penalty points, which will backfire in the end. So I just wanted to share this idea because with the segment tree solution, it's much more tricky, I guess. Yes.
How would you use that set to calculate the number of lumberjacks that fall in the contiguous sequences?
When I'm doing the update, or when I'm doing the update, I'm just maintaining some auxiliary variable values that tells me whether this chain has an even or odd number of elements.
Okay.
And you just only need to touch this value whenever there is an update, if you calculate it initially.
Yes, you would. I don't see. Sorry. How would you do so? I mean,
What do you mean? I mean, when you are using the set data structure, you can just always query the next special node, right?
yes.
And you know the
keep the
distance.
position
I
of
mean,
the-
you know the indices, so you know the distance, and you know that this is special. And up until that index, you have an alternating pattern. So that
But
you know
look-
the number, right? Or...
Looking through all the set in every.
No, you are maintaining a global value. You
Okay.
calculate it initially, and then you just maintain the changes to this value.
Okay. Yes. Thank you.
Wait, but like, so you're saying that if, okay, so if the time to follow the current one is I, sorry, not time to follow, but time to cut on the current one is I, or VI, sorry, and the time to cut on the previous one is V or VI, yeah. Then we know that this one will follow.
Yes.
Well, like, what about the case? Let's see, I think this thing like 411.
Like this.
Yeah. So like.
I mean, you can do this for all of them, right? I mean, then this is special, and
Yeah.
this is special.
But the one on lower right corner will cut down 4. And the 4 won't.
Nobody will cut down 4.
Okay, in that case I must have misunderstood it. Thank you.
I mean, these alternating patterns go from the special node to the next special node.
Yeah.
So he must stay. I mean, this is the same pattern. Okay, think it over, and we can discuss in the break. Of course, I didn't share all the implementation details, but so you might need to figure out like very small details. But I think this is like enough about this task. Okay. So next we had this coloring task. It was Baby Bob something. Okay, here we had a bunch of like nodes over a circle, and some of them were connected with some extra rules. And we wanted to find a coloring with 2 colors, so a bicoloring of the nodes such that we minimize the number of adjacent nodes with the same color. Okay, so let's look at an example. Okay, so we had something like this. If we want to, we might want to be very careful about the properties given in the statement for this structure, because you know that none of these like new edges, which are not on the perimeter, intersect. So there are no intersections. That immediately means something. That immediately means that these new edges cut this region, this polygon, into like subregions, and all of these new edges, as well as all of the original edges, are border edges of these regions. And there are like no new vertices because of no new intersections. And also a property that you might not spot at this stage, but will be very useful later on, is we had the extra property that each vertex will be connected to at most one other vertex. So there is no edge like this, or no pair of edges like this and this. Okay, which actually implies that every region here has at least one edge which is on the boundary of the circle. The only way to create a region that does not have a boundary edge, I mean, by the boundary I mean over the perimeter of the circle, sorry. The only way to do that is to have multiple edges starting from one of the vertices. But it's not true, so actually this is this is like this circle or this. Sorry, it's just not working. Yeah.
Can you try?
Yes, that's what I wanted to say.
Try.
Okay, thanks. Okay, so we get regions bounded by the old or the original and new edges. Okay, and every region has at least one old or original edge over the boundary. Okay, so if you are thinking about some very simple ways to do the coloring, so to color the vertices with two colors, you can immediately spot that there might be regions with having an odd number of vertices, and there are regions having an even number of vertices over the perimeter. So it is imminent that if a region has an odd number of vertices, then at least one pair will have the same color. Odd number of vertices, at least. Okay, at least one pair with same color. And if you have an even number of vertices, well, of course, it's imminent that you can have zero if you color alternatingly, but if you later want to prove the greedy claim that we are going to use, then you must realize that if you have an even number of nodes, it's not only true that the minimum is zero, but it's also true that the number of pairs with the same color is always even. Right? So even number of pairs has the same color. Okay, so at this point we can come up with a greedy idea. This I just put it this way because I might want to use it to prove what I'm claiming. Because what you of course would think, what you would want to do is you would want to have exactly one pair with the same color for the odd cycles and exactly zero pairs with the same color over the even cycles, right? That's of course a very natural idea. So let odd regions have one pair and even regions have zero pairs of the same color. Okay, and yes?
Does it not matter if there's one region is inside of the other, if they share the same perimeter?
I mean, this is not the solution yet.
Okay.
This is just one greedy observation that you can always enforce. Okay. Yeah, that will be the next one. But for now, you just have to realize that whenever you had an even cycle having more than zero number of pairs with the same color, then you can just essentially recolor it to have zero. That way you got rid of some even number of pairs with the same color, and that may, and in the worst case, that might create the same number of pairs with the same color on the neighboring regions. So that's how it's kind of working. You can argue that if it creates like a new pair with the same color in the adjacent region, then you can always do it in such a way that it creates a new pair with the same color over the boundary. So it is not possible to increase this way with recoloring the number of pairs with the same color. Okay, so this you might just believe, or you want to think about the proof. I just briefly said why it's true. This is the greedy observation that we need. So after that, we can say that, okay, let's suppose that now every even circle will have 0 pairs with the same color, and the even ones, well, the minimum is 1 for the odd ones. Sorry, for the odd ones, the minimum number they must have is 1. And it is obvious that you can achieve 1 for each of them, but they might have more in an unlucky scenario when they are having strange neighborhoods. I mean, no, sorry, my bad. No. You can always do it in such a way that they have exactly 1. You just essentially create one with the same, I mean, you just start coloring somehow. You can always enforce that the odd ones have at most 1, because you can just start with some coloring, and you can always ensure that the common edge has different colors. You can always ensure this because if you want to have 1 pair with the same color, you can always have it over the boundary, which edge is not shared with anyone else. So it is guaranteed that you can ensure that we can ensure that odd cycles have exactly 1, okay, by having it on an outer or old or original edge. By having it on an old edge, we can always create like a greedy coloring which has exactly 1. Okay, but actually we can do better. We can try to optimize it by rotating the coloring somehow such that the adjacent odd regions have share the pair of nodes with the same color over an edge. So that's what you kind of want to do in some cases. In the most simple case, when you have like 2 odd cycles, you can just think about having the same color like here. And so you just have 1 pair with this property instead of having 2 pairs. Oh, sorry, I didn't mean to erase this actually. Okay, so now we have some kind of a maximum matching problem, if you wish, right? Because we want to match as many of the neighboring odd regions as possible to pairs, such that those pairs are sharing an edge with the same colored vertices. We want a maximum matching between adjacent odd regions. And then, according to the matching, if two regions are matched, then over the common edge we will have 2 nodes with the same color, and everything else will be colored alternatingly. Okay, so can we say anything about this graph? because this is, at this point we didn't say much. At this point we might think it's a maximum matching problem on an arbitrary graph. Sorry?
Linear graph.
Yes, and?
Bipartite.
Yeah, it is bipartite, but actually the limits won't really allow us to solve that problem. Yes?
Regions form a tree.
Yes, this is actually a tree, which is of course also bipartite, but we actually are not going to use that. It is bipartite. It is a tree. So this is a tree, and we have to remove the even regions because we already decided that we will find an optimal solution that has 0 with the same color over the boundary. So this is a tree. We remove the odd with the even regions, so this is a forest. And we have to find the maximum matching independently on all the trees. So the regions form a tree. If we remove the even regions, then we get a forest. We want a max matching on a forest. This is like a very well-known problem. If you want to solve it independently, I think it's available on CSES or something like that. Yes?
In this graph, for example, you can't always just color the internal edges, right? Or it does always work if you choose only internal edges as pairs of the same color.
What do you mean I mean, over the perimeter internal, or but yeah, these.
Yeah.
I mean, for this one, yes, but this is a very tricky case because here you cannot match anything to anything, right?
Yeah.
So it's in general that's not true. I mean, here you actually this construction removes the root and you get 3 trees with a single vertex. So yeah, here it like doesn't matter what you color. If you obey the basic rules that we set, you get an optimum. So for this example, this is of course not so interesting. So yeah, you have to solve this max matching on a tree problem. You should try to figure it out yourself. It's an easy DP problem. I actually cannot remember. Maybe it actually has a greedy solution, but mostly we use it to teach like a simple DP on a tree. So.
Just a question, like if you did the DP without realizing the matching, wouldn't the complexity be the same? Because it's still a tree?
Sorry, once again, if
you don't realize like the pair, the even cycles, like can be always solved, doesn't the DP also work? Because
not necessarily, because if you start matching the even regions, I think that might become suboptimal.
I mean, but it's the same, like.
But the complexity is of course the same, because in the end you have to do a linear DP over the same number of vertices and edges. So, or just a small amount of less edges, but it doesn't matter. So, yeah. Yes.
And in the third graph, is there also a vector representing the external region? Or
you don't have to care about the external region, if that's what you mean.
yeah,
you can completely discard it. You are only interested in like finding matchings between these internal regions.
okay.
I mean, if you match something with the outside, it doesn't matter, because if you color these with the same color, then you can see that you can match any number of edges with the outer region, and also that does not improve the result that you are getting in the end. So you should just ignore the outside in that sense. I mean, in a solution, in a coloring that is constructed in the end, you might color some edges on the outside with the same color, because you might have vertices in the tree that are not matched to anyone. So that means that the same pair, the same colored pair in that node, if that node is not matched to anyone, then it means it must be shared with the outside. So it's a boundary edge in that case. Okay. Okay, if you haven't solved it, you should think about like how to implement it. That's also like an interesting question by its own. I haven't checked your solutions to be fair, but otherwise, when we originally used this problem, like there were two solutions that we came up with, and we didn't really see any other options. There is one way where you do it linearly, like do everything linearly. You can construct the tree structure by essentially simulating like depth first search. Sorry, somehow it was difficult to say. So you can simulate a depth first search by essentially iterating over the boundary, over the perimeter, and just take a look whether there's a new edge added from the current one. If yes, that means that you have to traverse an edge on the tree, so you can like put it to a stack, like if you simulate the DFS with a stack, not with recursive calls. So you can simulate the creation of the tree with a stack by doing a DFS by hand. Okay, that's one possible linear solution. Otherwise, you can maintain the coloring itself if you want to on the fly by using, like, I don't know, a binary indexed tree or some simple data structure. That worsens the complexity, but that's also a feasible option. Okay, so you can come up with multiple ideas. The implementation is very flexible for this specific task, I would say. Okay, next up, drawing. Okay, so this was not solved at the contest. This is, I think, a really interesting task in many ways. So this is a geometry task. If you are not familiar, we are given like a lot of vertices, at most 1,000 points on the plane. Okay, we are guaranteed, it is guaranteed that we are not given the origin, and it is also guaranteed that there is like no line crossing through the origin. Okay, and we want to create a drawing. A drawing is essentially a simple polygon which must have the origin in its interior, and we want to minimize the maximum edge of this polygon. I mean the maximum length edge of this polygon. So we want a simple polygon contains the origin and the maximum edge or maximum side is minimum length. That's minimum length. Okay, so actually there is more than one way to solve this problem, but I described the one first at least I described the one that I think is like more natural. I myself think it's more natural, otherwise you might think otherwise. But anyway, so since it is minimize the maximum type of problem, what's the first idea as always? Binary search. Also, the number of points was at most 1,000, so that kind of means that that you can create a vector of all possible edges and sort it. So when you do a binary search over this maximum, for any value visited over the binary search, so let's say you currently want to check a value L, then you can just select the edges, all the possible edges, all the possible pairs of nodes for which the distance is at most L. So select all candidate edges or sides, whatever. Okay. So first I will draw like a dream scenario, because if you just select a bunch of edges, it might be very chaotic, right? For example, here if I will draw all the edges, it will be very chaotic. So the dream scenario would be, I don't know, something like this. Okay, there might be something that I didn't draw here, but whatever here. But consider some case like this. So, so here, what we would like to do is quickly find whether there exists a polygon that satisfies the requirements. That's the only thing we care about. Check whether this L is like greater or smaller than the answer we are looking for, right? And I claim that we are able to do that with like doing depth first. This word is not my word for today. We will do depth first search in all components. And we just have to do it once in every component from one arbitrary vertex to give an answer. That's what I'm claiming. So I'm claiming that if I just, okay, here we will just do a traversal like this, and we should report that we didn't find anything yet. And here, if we start from like an arbitrary point, I'm claiming that during one single depth first search, we will be able to determine whether there is like a closed region containing the origin. Okay, so why is it true? If you are doing the depth first search, you will of course encounter cases when some edge you want to traverse points to a node that you already visited. And in that case, of course, you skip it in the depth first search. So if you are just thinking about visiting the nodes with a traversal, that's what would happen, right? Okay, so what I'm claiming is, even though this does not find like every possible region created by the vertices, it will find at least one that contains the origin if there exists at least one. And how to prove this claim? How to prove that that by this simple way of doing the depth first search and like always go back whenever we would revisit the same node twice, why is it guaranteed that if there exists a region containing the origin, this will find at least one? So the thing is, if you think about it, if you think about the tree of the created by the depth first search itself, and you create like directed edges in this tree from ancestor to child, go back, go back, go back, go back. And this is the point here. I didn't visit these. And this is the point where I should be able to tell that I found like a closed polygon containing the origin. Now, of course, this drawing with a single color is not ideal, but I don't know if you can spot some interesting property about the regions. The regions are bounded by edges pointing, all of them pointing either clockwise or counterclockwise. That's actually a very simple property coming from the depth first search itself. Okay, if you look at any region and see that this might not be true for an edge that creates a cycle, but it is true for the edges visited during the traversal. So in the DFS tree, you only had these kinds of edges, right? So then you can prove that you are guaranteed to find one, because just take any DFS tree, look at the origin, there must be an edge somewhere which was traversed, find that edge, and then based on the direction of that edge, just walk the tree in like both directions. I mean, you can always walk it towards the root because you know the ancestor, and you can always walk it some way forward. Okay, and this way you can guarantee that there exists at least like one cycle somewhere with an unvisited edge. I mean, with an edge that is not part of the tree. There is one cycle that contains the origin. Okay, so this is a bit tricky geometric argument, because you actually never do this algorithmically. Algorithmically, you are just happy to see that if you run the DFS and you close it down, then if there exists a region containing the origin, then this will find one. But of course, there are still at least two details missing. One detail that is missing is, how do we know whenever we encounter a cycle if it contains the origin or not?
Can you do something like for each edge, keeping track of whether the origin is on the left or on the right? And if you, when it closes, if all the edges have the same color.
In what sense do you mean left or right?
Like the 2D cross product?
Like this, sorry?
Like the 2D cross product? Like whether you have to turn to the left or to the right?
But I mean, compared to what? So okay, you always have an edge, but what's the other vector in your product?
The origin, like
but the origin is just 0, 0. It's a point.
Yeah, but you project the origin into the.
Yeah, so you mean the line, and on which side of the line? Okay, sorry. So you mean that you extend the line?
Yeah.
Okay, yeah. Sorry. Okay, I see. Okay, does that work?
And the cycle like snake.
I mean, I think if it's concave enough, it won't work actually. Yeah, something like that. So you can see that. I mean, even in this example, maybe you can. But you can just change this side, right? I mean, it is on one side, and this here should be on the other. Okay, so sorry, maybe I overcomplicated it, but the main point is, if you just count that property, then like you can have a bunch of these, and for the last one you can just like rotate it a bit to change the parity of the kinds of edges. Okay, I mean this might be not the simplest example. This is what I came up with on the fly. So anyway, it does not work. But actually, this is a very good example of the concept. One of the concepts I'm trying to teach you this week. That you should always try to understand your library a little bit. So because for example, if the question was, and I think many of you solved the task like that. If you are given some polygon, and you have to decide whether a point is inside or outside. How you solve it? From the point you cast a ray and count the number of times it's crossing an edge, right? Right, from here you cast a ray towards infinity and count these guys. Okay. So, in this algorithm, we don't have time to do this, because every time you find a cycle, if you run something like this, that will be very slow. But how can you do it efficiently? Just cast a ray from the origin before starting the DFS, and then when you add edges, count the number of times they cross this. And you can maintain it. I mean, you can maintain the previous value for some internal node of the DFS tree, so when you step back, you don't need to do anything like tricky. So cast a ray first, or before DFS. Count intersections. And you know from the number of intersections, whenever you find a cycle, whether it encloses the origin or not. Okay, and there is still one thing that is actually like a minor thing, in the sense that if you forgot about it at this point, then your implementation will still pass. But the problem was asking for a simple polygon. So it means it must not intersect itself. Right? And that's a dream scenario in that sense, because I didn't draw any edge that is intersecting with another edge, but it might happen during your binary search. So how to deal with that? Well, the answer is don't deal with that. And the reason for that is, if there exists a polygon that contains the origin and crosses with itself, and we are looking for the one with minimum length, then we can find one that does not cross itself and has at most at that, and the maximum is the same or lower. How to do that? How to do that? The intersection is between two edges. So consider this, not this. So consider this rectangle formed by those two. This is actually a parallelogram, you know, it must be because you are essentially given the two, what's the English name? Oh my God. So really? Yes, that, and you just complete the parallelogram from it. So what I'm claiming is, here we have the two. Here we have the two edges connecting the vertices across. So you can remove at least one of them without changing anything, because, for example, because there is one side because at least one of the two sides has smaller length than any of these two. So, for example, you could either remove those and just do this, or if it's not working, I mean, if this is worse, then you could keep this and do it this way. I think that's the only two cases that you have to care about. Though you can actually choose to keep the other one instead, so you could also consider this going this way. But actually, this way you are guaranteed that you can remove the intersection by removing one of the two intersecting edges. So the solution does not have intersections, or at least there is an equivalent solution not having intersections inherently, so we don't really have to care about this. Okay, and that solves the problem. We now have everything. So So actually, this is something like n square log n square times log in complexity. So this is a pretty good way to do this. You can optimize it a bit because instead of doing this DFS, you could you could actually skip the binary search itself as well. You just select the edges, sort them, and start adding them one by one in a disjoint set union. And there you could adapt the same trick. I mean, you kind of use the same idea, but you have to be careful to somehow be able to detect whether there is like a closed region containing the origin. So you have to contain some intersections, some number of intersections with this ray as well. So there are things to consider during the implementation, but that's also a way to solve it. Okay, yes?
Sorry, could you explain again quickly, how do I check if the origin is inside the polygon class? I didn't understand like what rays would you cast like before?
So this is an almost arbitrary ray, but you should of course make sure that it does not overlap with one of the edges or something like that. So what you can choose, for example, if this is 0, 0, and so the points had the coordinates like between -10 to 9, +10 to 9 or something like that. So you can just select like 10 to 9 plus 1, 1. And then it's safe to say that that each edge is like either not crossing it or crossing it. There are no overlaps. And there are also, sorry, not just overlaps, my bad, but there are no points on this segment, because that would make the implementation a bit more tricky if you had to deal with the case when there is a vertex here. But this also won't happen, because this line doesn't go through any of the like grid points. Okay, so you think, or you just save this ray or save this segment, and then in each step of the DFS just check whether your current edge crosses it, has an intersection with it, and maintain the parity of this. Okay, if you are a huge geometry fan, then you can actually think about like finding an n log square solution or something like that. I think that's the best solution I came up with back then, but actually it's super difficult in the sense that you need to reduce the number of edges that you consider by like a magnitude. And you can actually do that, but it's pretty difficult. I mean, the proofs are pretty difficult. If you from each point, if you cut the plane into like octants, so like eight like regions, then you can actually find an argument that allows you to throw out most of the edges and just consider like a constant number of edges going out from each node. So it can be improved, but that's, I don't know, that's probably close to like Word Final's most difficult problem level. Maybe not, but somewhere around the top 2 problems in the problem set. So that, and I think it's not that beautiful, but I'm not a geometry fan myself. I think this is beautiful, but whatever comes after is just.
One question.
Yes.
I didn't get the last part. Can this problem be solved by considering only a subset of edges?
Yeah, so the idea is just to reduce the number of edges that you consider for each point to at most a constant number.
Okay.
And it's not easy. I mean, first you think, yeah, it's natural, but there might be some scenarios when there might be more. But then it turns out that if there are more, then of course those should be connected in a solution somehow. So it's actually, I think, pretty hard to prove. I cannot even recall it now by heart. I did it a few years ago, so I safely forgot since then. Okay, next, deer dance. Okay, this problem is pretty cute on its own way. There are actually two ways to solve it, and there are like interconnected ideas between the two of them. So let's look at an elementary solution first. Okay, do you remember the task? The task was that you are given like a tree. Okay, you can put like some decorations of two colors into the vertices. You are allowed to put many of them to the same vertex, but the condition is that well, we had two conditions. First, none of the vertices can have like both kinds of decorations. Okay, all the decorations of what was the color? All the decorations of green color must be like towards the leaves, and all the decorations with red must be closer to the root over any path. And additionally, over any path from the root to a leaf, you must have the same number of red and green decorations. Okay, so by nature, this is actually some kind of a combinatoric task, but it is difficult in the sense that that you have to guarantee that any path has the same amount of like decorations. So you cannot you cannot naturally break down the problem into sub-problems and solve it in the smaller trees. I mean, you can do something like that, but you then still need to somehow combine them. So that's like the main difficulty. So for example, in this case, these two had green. I'm just copying the example from the statement. That's I am. I think it was like this. Yeah. Okay, so this is an example of a valid decoration, right? So what I'm going to do is think about the placement of the decorations as placing them into some kind of layers, because by the property that there is the same amount of red and green decorations over any path, it allows us to create layers in such a way that actually they each contain either red or green decorations, and each layer contains like exactly one of them in each subtree. Okay, it's easier to draw this. So this will be the first layer with this red decoration. This will be the second one. Should I index this? Yeah, this will be the second one with the red decoration. Now the third one. So the third one contains, yeah, that's what I wanted to say. The third one contains the third decoration in each path. Okay, and the fourth one contains the fourth decoration over each path. Okay, so just to make it easier to talk about it, we can easily like describe some relations between these layers. So for example, if two layers pass through the same set of vertices, then we can just claim that they are equal. Makes sense, right? For example, the first two here are equal. Okay. You can also claim that some layer is like greater or lesser than another one by saying that it is like lesser than if there is at least one vertex that goes like closer to the root. So what I'm saying that, for example, if you look at this 3 and 4, they might have some vertices in common, but if there is a vertex that is not common, then one of them has this vertex closer to the root, and one of them closer to a leaf. So in this case, I can say that, for example, 3 is lesser than 4, because 3 runs overall closer to the root, but there might be some equalities. Okay, and finally we have, for example, between 2 and 3, this strict inequality in the sense that all of the vertices here are closer to the root than all of the vertices here. Okay, so this means at least one vertex closer to the root. And this means all vertices closer to the root. Okay, so what we are looking for is actually like a set of layers, but the number of layers could be huge. I mean, the number of layers will be like R plus G, where R is the number of red decorations that must exist over any path, and G is the number of green decorations that must exist over any path. Okay, sorry, if you are not familiar with the question of the task, the question itself is for a given R and G, compute the number of ways to decorate the tree such that every path has exactly R and exactly G decorations with the given colors. Okay.
All the paths have the same amount.
Yes. Yes.
Okay.
So this means that we are actually looking for the question is to find the number of choices for layers, of layer sets. Find the number of layer sets such that, okay, so you can see that you start from, I don't know, let's notate it by A. Okay. So you have the first layer. Then you have the second, the third, the fourth, and so on. So there is, in the end, you will get R plus G amount of layers, right? But there is one very important point here. So between the layers, naturally speaking, we can have greater or equal relations, supposing that greater also includes this case as a possibility. There is only one step in this chain of inequalities when I cannot write lesser or equal.
Between R and G.
Mm-hmm. Where the red layers end and the green layers start. And by construction it is at AR and AR plus 1. Here I must have the strict inequality. So I'm looking for the number of these kind of layer sets. And what I'm doing here is observe that, okay, R plus G is huge, and you can almost always find this kind of configuration. But what I'm claiming is the number of cases in this chain of inequalities where we have like a strict inequality cannot be that large. So the first observation is that the number of strict inequalities is at most, can you tell me how many? Like an upper bound. Sorry? Huh? What? Depth, yeah. Not, because I'm just talking about the strict inequalities. So you can just, for example, take the fourth one, take the third one, then advance here. That's also strictly smaller. So that way you can create more than the depth, but close. You always need to move somewhere at least one vertex deeper. So it is bounded by the number of vertices. And of course, in the statement, the number of vertices is at most like 300 or 500, something like that. So what we are going to do is we are going to do dynamic programming on the tree, and we just want to find the number of configurations having a given number of strict inequalities, which can be 0, 1, 2, and so on up to n. And then after we have that, we will distribute the balls or decorations. I don't know if it was balls or whatever. We distribute the decorations by essentially saying that, okay, the rest are equalities, so we just put a bunch of equal decorations, equal layers between the ones with strict inequalities. So what we are going to do is like count some sequences with strict inequalities. Like AK1, AK2, and so on. This kind of sequences, but be careful because there is that splitting point between the red and the green. So of course there should be a breaking point somewhere, after which comes a r plus 1 greater like a, I don't know, L1, a L2 with strict inequalities, and so on. Okay. Something. So because of this thing, I will break it down into two parts one more time, because it is like kind of difficult to do with just a simple DP to also maintain whether you already crossed the limit or the threshold after which the other kind of decorations come. So first, I'm just doing a DP for this. And then I will do the rest of the work with the second one. Okay, do a DP for this. So what I'm going to do is, let's say, DPG. I'm calling it G because you see that it corresponds to actually green decorations. So DPG for like VK will be the number of ways, the number of layer sequences with strict inequality of length k in the subtree of V. Okay, this step is kind of natural, right? If you finally want to do a DP on a tree, it's natural that you will solve it for the subtree of the given vertex, and now we know that the number of different layers, the number of layers with strict equality is bounded and not too big, so it's natural to count this. Okay, of course, the DP transitions still need like a little bit of work. And so if you start thinking about it a bit, I'm not going to go through like the whole process of thinking, but actually you easily find out that it's by itself this is difficult to calculate if there are like there are cases when there is a layer going through V itself. Because if there's a layer going through V itself, it might be difficult to merge a subtree with the root vertex, something like that. So actually, it's I think implementation-wise, it's worth introducing like an alternative DP, which is the same number, but we say that V is not among the layers. But V is not a layer or not on a layer or whatever you wish. Okay, you will see that this is easier to calculate. Of course, during solving the problem, you encounter it differently. You find that it's very difficult to merge the subtrees, so you come up with this idea. But this idea is common in DP on a tree problems, at least I've seen, like, I don't know, lots of them. So okay, so this is actually not too bad. I mean, if we had this, then the actual answer is not that difficult to retrieve, because if we compute these values, then in the end we can just say that the original DPG that we wanted to calculate is DPG prime VK. These are valid solutions. These are the ones that does not have V as a layer, plus DPG prime VK minus 1. These are the ones that have K minus 1 layers below V, and V must be the plus 1 layer. Okay, so it is indeed enough to consider the case when V is not a layer. Okay, let's try to figure out the update, how to merge subtrees, how to calculate the DPG prime. So first, DPG prime for VK over like a recursive solution. First, if we process the first subtree, we can just initiate it as the value of the first subtree. S K there, where the parent of S is V. So this is for the first subtree. For the first subtree. And then, after you process another subtree, you have to combine the results of the two subtrees. That's the interesting part. How to update after further subtrees? So the thing is, if you think about it, you have the counts for both subtrees for all different number of different layers, and you want to merge them. Now it is important to observe that, for example, if you consider the case when, of course, both of them has the same number of different layers, then you can just try to merge those. But you can also merge the subtrees when one of them has like a smaller number or greater number of different layers than the other. Okay, because, for example, if in one subtree you somehow have, like, let's say, 2 different layers counted or enumerated somewhere. Yes? And in the other one, for example, you have like 3 of them. Then when merging those two, you can actually create some new layerings by saying that, okay, some of these, let's say, like, continue with copies of some of the layers, and this one is, for example, connected here. Or you can introduce a copy of another one and say that one continues here, one continues there, and so on. Okay, so these also create new valid solutions. The thing is that here you can then consider like having p number of layers coming from the one subtree or the already counted like few subtrees that you already merged, and you can have some other number of q different layers coming from the other subtree. Then you would have something like, okay, so one of them is the cumulative value that you already have in V. This comes from the merging of all the previous subtrees, or initially only the very first subtree. And from there you take P different layers. Okay, from the other one, this will be the newly processed S subtree. S subtree. And from there you will take Q. So that was the easy part in some sense. We want to combine them. Okay, the question is, like, how many ways to do this? To obtain k layers, that's important. K different layers, to be fair. Okay, there is like one more case that I haven't really mentioned here is that, is it? No, okay, yep. So the thing is, you need to somehow distribute these p layers on one side to these k available layers that you create after merging in such a way that each of them can contain like an arbitrary amount of them. Yes, and you have to decide like how many of these will be connected to the other side. So for that, we can have a formula like, let me think it over just a second, like minus 1. Something like this, I think. Maybe I'm off by one, but the idea is the idea behind the formula. If you think about it, it's there are these kinds of formulas. I'm not sure you are familiar with them in combinatorics, where you want to substitute some number of balls to some number of boxes, and there are various like different variants, like if every box shall contain at least one, or it doesn't have to hold, and stuff like that. So we have to use some similar argument here, and this is something like we are going to create k layers. Let's just index them from 1 now. So let's see. Okay, so we are essentially considering the 8 layers that we are going to create, so k equals 8. And first, what we can do is, let's just distribute how those layers will contain the p layers coming from this side. And from there, and for that you can just consider the layers, the layers to be created, and select and select like the points where you like put these layers from P. Yes. And then you kind of repeat the same idea, but now with these P layers and the remaining layers plus the potential extra layers from the other side. Yes. Okay. Yeah. This is actually a tricky one. You should try to think it over. It's not super obvious. I mean, if you want, you can expand the formulas a bit to see it's true, but yeah, okay, this should work. So this should work, and then this means that this is actually a negative one, but this is just a minor detail. Okay, so this way, with a combinatorial argument, you can compute the ways how to combine like P layers with Q layers to create K different layers in the end. Okay, for that you must find some formula like this. And with this formula, we can actually solve this first DP problem. Okay, I have to hurry up. So you can solve this DP problem, and after having it, so after finally having these DPG values, you can also consider like the number of ways how you can distribute like the green decorations to them. So you don't want to so after computing this DP, and let me just collect my thoughts. Yes. So after completing this DP, now you know this number of ways to select the different layers. So after that comes the second part, and the second part is these DP values can be used for distributing the green decorations, and after that you have to continue and do something very similar for the red ones. To do something very similar for the red ones, you should, for example, calculate a very similar dynamic programming if you want to. You can do something like dprvk. This will take into account now the red part of the thing. For this one, you can define it as the number of ways to do a very similar selection. To do a very similar selection for some number of layers, actually k layers, that will contain the red decorations, and then have a strict inequality here. And you can immediately like use the previous DP values for this part, just calculate this AR plus 1 greater or equal AR plus 2, and so on greater or equal AR plus G part. So, for example, you can consider this DP. This is a good idea in the sense that for the updating part, the merging part, it will be essentially the same. So for that part, you don't really have to think about anything. The only thing that's a bit different is the initialization of the DP values, because you actually want to initialize, because you actually want to initialize by saying that, for example, okay, I don't have any layers yet in this part, but I already need the count of this part. So here here you should take once again this very end where you remove the vertex and just consider the layers beneath V and initiate it somehow. So to initiate it, you actually have to like consider the ways to put these G decorations into some number of layers in any way. So here you just have to take some summation over the previously computed DPG values. Of Vx. Okay, and what you have to multiply with is very similar, actually even simpler than coming up with the number of ways to merge them, because here it's the more simple case when you have some number of layers and you have to distribute G decorations such that each layer contains at least one. So actually this is the simpler combinatorial argument, and the combination part is the more tricky one. So here to do it, just consider the D1, D2 and so on, DG, G number of decorations. You have to distribute them into X layers such that each of them contains at least one. So what you should do is once again consider the potential like separating points. These separators mean that if you select one, then up until that point you will have one layer, and after that you have the rest of the layers. Okay, and so it means that you have to choose like, so this is G number of decorations, so the options for separators is like G minus 1, and well, it depends how you do the DP. If you do how I just wrote them, you have to select, of course, not of course, sorry, you have to select, sorry, X minus 1 separators to create X layers, okay, yeah. So something like this is how you can initiate it, so that part is taken care of. And after that, you repeat the same kind of transition when you merge the subtrees to have the different numbering, to have the enumeration of the red layers, and in the very end, you distribute the red decorations into those layers. That is almost the same formula once again. Okay, so this is like a very elementary way to solve it, I would say. This combinatory part is a bit tricky, so it is not easy to solve, of course, by any means. Otherwise, the same argument is easy to repeat if you have more than one colors. So actually, it's an interesting property here that if you actually would have more colors than this, then you could just keep repeating, adding these strict things, so that will just add a multiplier with the number of colors. Okay. Anyway, what is our complexity? Well, because of this merge, which can take like n square operations, the complexity here is n cubed. So this is a relatively slow DP. An interesting property is that it generalizes relatively well to an arbitrary number of colors. Okay, so there is of course other ways to solve this task by less elementary means. It mostly involves some form of experimenting. The other thing that I was like talking about over the past few days, that if you start to experiment, you might notice something that is familiar, some interesting relation. And because it's already break time, maybe I will just explain in words for now. So you might discover that if you have some specific configuration, for example, if you have like a V-shaped tree, then you can easily spot the relation between like sums of powers of numbers, like for example 1 to p plus 2 to p plus 3 to p and so on, summed up in finding the number of ways as an answer. And you already know that these kinds of objects, when this happens, when you add, for example, a given powers of the numbers, I don't know if you know what's this problem called, or what is the formula to, or how, or what's the name of the formula to deal with it? Does who knows this problem in general? Compute the sum of the power of given powers of natural numbers. Okay, not everyone, so maybe it's not worth explaining in too much detail. But those you know that this problem can be solved efficiently in the sense that if you fix the exponent, then it doesn't matter like how many numbers you add. You can add the numbers from 1 to, I don't know, 10 to the power of 9, having the same exponent. The answer can be calculated as the value of what? Of a polynomial where the degree depends on the exponent and not the number of values. So it's to say it's a polynomial of the exponent and not the number of terms. Okay. So if you experiment a bit and spot that similar numbers may appear, then you might get the idea that the actual answer, even though it depends on R and G, the number of red and green decorations, it is actually a polynomial with degree at most n, the number of nodes. And from that point, you can actually simplify the problem. Because if you have this knowledge that the answer you are seeking for is a polynomial with some degree n, in two variables, R and G, then how can you get this polynomial? And don't worry, I'm not going for FFT this time. Okay, about half of the group knows it, about half of them not, but the answer is, if you want to compute the polynomial, a simple way to do it is to do it by so-called interpolation, which is like a scary term, but it only means that, okay, you want to find a polynomial, and then, so you have a polynomial in R and G, you know that the degree of P is at most like n or n plus 1 or whatever, something like this. Then if it would be a polynomial in just a single variable, then what you would do is simply try to evaluate the polynomial for 0, for 1, for 2, for 3, for some simple values. And then if you have, let's just suppose the polynomial has degree at most n, so if you have at least n plus 1 points, they uniquely determine the polynomial. After you have the polynomial, you can compute its value for large R, let's say, by just substituting large R to the polynomial. Okay, and here you don't need to use any advanced techniques in the sense that n is at most 300. So it means that you can do like a relatively naive like m square or even m cube way to do the interpolation, and then the substitution, for the substitution as well, you can just like naively substitute into the polynomial. You don't need some fast substitution ideas. The only thing that might be an issue here is this is essentially like a two-variable polynomial, so you have to deal with that. A basic way to do it is to just do it in 2 dimensions, like compute a 2-dimensional polynomial. That's one feasible way to do it, because the constraints actually allow it. You can compute the values over a grid and use that, or you can also simplify it a bit, I believe. But yeah. Okay, and finally, like how to get the values of this polynomial? Well, since you just need like O(n) number of values, it means that it is enough to solve the problem with the number of decorations at most n. And for that one, you can use like a much more simple DP. Because then you can do a DP where you keep track of like the remaining number of decorations you have to use from a given color. So actually you don't need any combinatorics. It's a much more simple DP problem, much more standard DP problem, you can say. Okay, so that's the other way to solve it without going much into details, because if you don't know these concepts, you should read about them, because I cannot explain in 10 minutes. So, yeah. Okay, let's have a break and let's meet in 30 minutes. So at 10:45. Thanks. Okay, welcome back. Let's start with the second part. So we are in a situation where there is like one more task that's worth discussing. It is in boxes, the data structure task. And I also wanted to like briefly introduce one more topic to like continue with the things that we are doing over the week. So what I will do is first let's just talk about this particular topic. I wanted to go like a bit forward with the maximum matching and consider like a base case of maximum flow. And hopefully I will have time to talk about inboxes in the end. Okay, if not, maybe we will see what happens. You might ask about it, or I might talk about it on another class, but I'm not sure. Okay, so maximum flows. Okay, so what is the flow problem? We are given a directed graph with edge weights like CE, okay? And we have a node or vertex S with 0 in degree and a node T with out degree equals to 0. This node S is often called the source, and this node T is the sink of a network like this, because the main idea of the problem, let's say this is S, okay, let's do something like this, and this is T. The main idea is that these edge weights, usually interpreted as capacities, that's why I'm using the letter C for them, and let's say this is 20, 20, 20, 20, and let's say 10. Okay, so the main idea is these capacities can be interpreted as allowing some amount of data flowing through the edge, or you can say a simple like real-world implementation is to allow some amount of water flowing through like a water pipe. Yeah. Okay, and you somehow want to model the problem where you can you can push any amount of water through S into the network, and you want to get like the most amount of water through to T. Okay, given that you have these capacities. So that means if you think about it like that, then of course if some amount of water goes from S to some other node, then it must go forward and go to another node and another node and another node until it ends up at T. So there's a condition that any water or any data that leaves S must arrive at T at some point. Okay, it does not get stuck in any of the internal vertices. So a condition. So suppose that, okay, one condition is that over any edge, the amount of flow that can go through is at least 0 and at most the capacity. The so-called flow going through edge E is, let's say it is FE, and it is between 0 and CE inclusive. Okay, this flow, this amount of flow is notated by F, so that's a new notation, right? And the other condition that I just explained, that in the internal nodes, if some flow enters, then the same amount must leave. Not necessarily through one edge, but somehow. It can be interpreted as if you add the flow values over the edges that enter some node, edge 2, some node, let's say V, So if you take all the edges that go to V and sum the flow through them, it must always be the same as the sum of the flow values over the edges that go out of V of the same node. Each from V. Okay, and here of course V is any vertex except the source or the sink. For S and T, of course, it works differently because, as I said, any amount of flow can enter through S and any amount of flow can arrive at T. So for those two, we don't have this kind of a condition. Okay, do you understand the problem? Yep. Okay, so you can try to think about solutions that are like similar to the ideas that we used at maximum matching. In maximum matching, we started from a greedy solution, like match through an edge whenever it's possible, without the augmenting paths and other ideas like that. And we easily saw that the greedy idea does not work. We had to improve it, and our improvement with the augmenting paths worked in finding the maximum amount, the maximum flow, where the maximum flow is the maximum amount of flow that can enter S, which is equal to the amount of flow leaving through T. So we want to maximize the amount of flow entering S and leaving T. These two values are the same. So the problem is, of course, to maximize the sum of FE edge from S, which is the same as the sum of FE through E edges that are to T. This is what we want to maximize, okay? And now, if we look at this example, you might think about like a very greedy idea. You can like start from S, try to find a path which goes through edges that have like unused capacity left. So you might just say, maybe this is a small example, so it does not hurt if I like redraw it. So you might interpret it as currently or initially there's zero amount of flow going through these. Right? And you can try to find a path from S to T using only the edges that have remaining capacity, that are not at full capacity. Currently, nothing is at full capacity, so you are just looking for any edge from S to T. Okay, and yeah, let's just suppose that, for example, you find this one. If you find a path like that, then by how much can you improve the flow of the network? Here by 10, if you just note down the available capacities over this path, then you can increase the flow by the minimum. Okay, relatively obvious. So increase flow by 10 over every edge that we traverse here. Right? Okay? If you can understand it, then we arrive at we arrive at this state. So now this will have like 10 out of 20, 10 out of 10, 10 out of 20, and the rest will be zeros. Yes. Okay, so um, so after this, if we this is I think also a counterexample to repeating it greedily not necessarily works, right? I mean, if we repeat it a bit more, then you can find that, for example, through this path, you can send 10 more flow, because here the remaining capacity is 10, right? Don't know. In the meanwhile, I'm trying to find some pen that is usable. Yeah. So here you can send, like, because the remaining capacities are 10 and 20, so you can send 10 additional more. Okay, so after doing that, I don't want to draw it, redraw it all the time, so after doing that, the flow increases by 10, so this will become 20, this will become 10, and that's it. And then, so I cannot use this edge anymore, I cannot use this edge anymore. If I do this one last time up here, then I can once again increase by 10. Right? So finally, I will have 10 out of 20 here, 20 out of 20 here, 10 out of 10 here, okay, 20 out of 20 here, and 10 out of 20 here. Okay, this is a possible termination of the greedy algorithm, right? Okay, so at this point we cannot find a path to the sink using only edges that have remaining flow that remaining capacity left. Is this maximum? No, because you can see that if you send 20 flow here, 20 flow through here, that's 40, and this way we only managed to do 30. So we've managed 30, but the max is 40. The greedy doesn't work, and actually, okay. And actually, you might notice that this kind of greedy approach that we used here is essentially the same greedy approach that we used for maximum matching, because, well, it is kind of well known, and I can also show it easily, that the maximum matching problem can be interpreted as a maximum flow problem. Because if you have a maximum matching problem, you can just take the bipartite graph, direct all these edges with capacity 1, and add a new source. This can be of infinite capacity if you want to, it doesn't matter much. They can be of unit capacity as well, because you know that not infinite, sorry. This should be unit capacity. I was thinking about the other side for a bit. This should be unit capacity because for each vertex you just want to match it with at most one other node, and this guarantees you that. To each of these vertices you can push at most one unit of flow, so you can get at most one pair for each of them. Okay, and the same way we can construct the other side with T. Okay, so any maximum flow in this is maximum matching in the original graph. And conversely, any maximum matching can be turned into like flow going through the edges in this interpretation, so it is equivalent. Equivalent max flow problem. Okay, so if you remember how we solved the maximum matching problem first, you can immediately get the idea of a solution to the maximum matching problem, because here if you like match the edges like greedily somehow, so for example if you match this, yes, it's a good example. So here with a greedy way you could find this maximal matching, which is not the maximum matching, and our algorithm would detect that it is not the maximum matching. How? By finding an augmenting path here. I'm experimenting with the colors, though they don't work that well. So this is an augmenting path. Okay, so if you think about this augmenting path as what would happen if you consider it in the flow setup when you try to find a path from the source to the sink, then you would see that the path would go like this. It first goes there, then goes there, and then somehow over this edge, which has full capacity because it is matched, it goes backwards, and then forward on this edge which has an empty, a free unit of capacity. Then it goes back on an edge that has like full capacity, and then it goes there again, and from there it finally can enter T. Okay, it couldn't do it earlier because for matched edges, these are at full capacity, or they also say these are saturated. Okay, so it seems like the idea here is to, in some cases, allow to traverse the edges backwards. Actually, you can immediately spot what's the use case of that. You should be able to traverse an edge backwards if it has a positive amount of flow going through it. Because if it has a positive amount of flow, then the idea behind the augmenting path here is that if it has a positive amount, you might reduce it in favor of pushing it through in some other way. Okay? So the idea that we learned from here, from our previous solution, or our solution to the max matching problem, is that we should allow backward traversal on edges with positive flow. Okay, and so in this case, when we got stuck, it would mean that we can actually allow some kind of a backward traversal here, actually over every edge essentially. Okay, and so this way we would be able to find a path that starts from here. It can go here forward because it's not at full capacity. It can go down here because it is because there is positive flow here through here, and finally it can go there because it is not at full capacity. Okay, so if we allow this kind of traversals, then we can find a path here. We just have to decide what to do with this path. Like, is it really possible to increase the flow by considering this path? And the answer is yes, it is possible. And we do the same augmenting idea as we did for the maximum matching, which means that if we traverse an edge backwards, like there in the matching, then we will remove that. In that scenario, we removed it from the matching. In this scenario, we reduce the amount of flow used over that edge. And where we push forward, those edges will be added to the matching. So here we increase the flow by that amount. Let's try to interpret what does that mean. Here our available capacity was 10. Here it was 10 because we had plus 10. The positive amount of flow through here was plus 10, so our capacity was 10 when traversing backwards, and here our capacity was also 10. So it seems like the magical number is 10, and if we do what I told you, what is analog to the maximum matching solution, we increase the flow here by 10, we decrease the flow here by 10, so this will become 0 out of 10, and this is a forward edge, so we increase the flow by 10. That's just the naive copy-paste of what we did at maximum matching. But now we can see that it actually creates a valid flow network. It creates it because here, where you remove the flow, you could say that, okay, over a backwards edge, you remove the flow, but since on the forward edge you increased it, you can think about it as sending this new 10 amount of flow through the rest of the original path. So you increase here by 10, and now that 10 units of flow will go to the sink this way, because now this 10 units of flow doesn't have to go to the sink this way. So you essentially just replace this 10 flow this way with 10 flow this way. Okay? And so here you put 10 amount of flow back here, so that must somehow reach the sink. But since from here we found a way to the sink with at least 10 units of capacity, so we can just move these 10 units of flow to the sink with the path that we found. Okay, so whatever is pushed back, it will be pushed through the rest of the path that we found, and the rest, so when we traverse a backwards edge, and the rest of the flow that's got stuck here will traverse through the original path of the flow that we removed. That's the idea, that's the bijection, which proves that this works. Okay, bijection, I mean we bijected the units of flow to where do they go in the original and in the new setup. Okay, do you understand? Questions? Yes?
Okay, so we know it works and it generates a valid flow, but how do we know it's a maximum flow?
Yeah, that's the rest of the story. So now we have an analog way to do augmenting paths. You can call a path like this an augmenting path in the flow setup. It doesn't have to be like alternating or anything like that. That was very specific to the max matching, but you can see that it can use forward and backward edges with the given definition. So we should try to somehow argue that what this creates, if we apply it repeatedly, will actually be a maximum flow. So the best that we can achieve. Claim iteratively we find maximum flow. Okay, actually there is a question even before that. Can you prove that this terminates ever? I mean, it does not seem obvious, right? You can just search for it, find something. Maybe you can do it like infinitely. That's it. It's a sequence of integers. The amount of improvements form a sequence of integers in this case because it has like integer capacities. Let's just stick to this case. So yeah, it is bounded. So it must terminate. Can you tell me an upper bound?
Some of the capacity.
Some of the capacity is very good. It's an upper bound. Okay. Actually, there is an upper bound for which we can prove that it is the best upper bound. But at first, we should just see that it is an actual upper bound. So first, we know now that it is terminating. Terminates. Because it is an increasing integer sequence. Upper bound. Okay, and actually the key point of like realizing how efficient it is and why is it working is to realize that there is an upper bound which is always considered the dual problem of maximum flow. The upper bound is a so-called an upper bound is a so-called minimum cut. Who knows what is a minimum cut? Most of you heard of it, okay? Actually, not just the so-called minimum cut, actually any cut in the flow network is an upper bound. Let's just first see this. Cut is upper bound. Okay, what is a cut in a flow network? A cut is like the arrangement of the nodes into two disjoint sets. I mean, no, there's an easier way to define it. So an easier way to define it, a cut is a set of edges such that if you remove that set of edges, then the source and the sink would be in two different components in the directed graph. But you can also define it like a bit of a converse way. So it's either you can say that it is a set of edges that after removal creates different components for A and B, or S and T. Okay, but you can also define the cut in like a converse way. Sometimes it's useful to understand that you can also define the cut as creating two vertex disjoint components, one containing the source, one containing the sink, and then if you remove any edge going from A component to B component, creates a cut, right? So consider A subset of V, B subset of the vertices, S in A, T in B, A and B disjoint. And that's it, and then remove any edge from any point of A to any point of B. Remove any edge from A to B. Okay, can you see why any cut, if we consider the measure or the weight or value of the cut, the total weight or total capacity of the removed edges, then can you see why why any cut is an upper bound to any flow? Okay, yes?
To saturate the edges on the cuts, no flow can pass through from the source to the sink, so it terminates.
Exactly, that's it. You can consider the case when every edge in the cut is saturated, is at full capacity, and then you cannot find a way from S to T such that it improves the flow. So yeah, that's it. Okay, so any flow is lesser or equal than any cut. Okay, and so after that, what you can do to prove the feasibility of this algorithm is to say that let's consider the minimum cut. A minimum cut. Okay, let's consider a minimum cut, and then let's prove that this algorithm eventually reaches the value of the minimum cut as a flow from S to T. So we can prove that the amount of flow reached by this algorithm eventually will be equal to the minimum cut. And because of this inequality, which is true for any flow and any cut, it means that that is a maximum flow. Okay, that's the abstract idea behind this. So if the algorithm reaches a flow equal to the minimum cut, then we have the maximum flow. Okay, this is clear from the inequality between the sets. Okay. And at this point, I'm kind of happy to skip the proof, not because it is difficult, but because it is actually easy. I mean, you can easily prove by contradiction if you suppose that there are some unsaturated edges over the minimum cut, then there exists some path. So it's actually relatively easy to do. This observation with the relation with the minimum cut is kind of what made this made this problem difficult. At this point, the proof is technical, so let's just save time and then you can try to figure it out for yourself. It's also easy to look up, by the way. This means that we got an algorithm. Okay, we iteratively try to find an augmenting path, increase the flow, and then reset and do the augmenting path. Be careful that in this particular algorithm you have to maintain the edges and the backward edges at the same time, and if the flow changes on an edge, you have to modify the capacity of the backward edge and so on. So you always have to work on these pairs of edges naturally. Okay, does anyone know what's the name of this algorithm?
Ford Fulkerson?
Ford Fulkerson, excellent. Okay. Can you tell me a theoretical upper bound for the complexity? Yes, you can search the augmenting path in using a DFS or BFS, so it's like O E plus V for each iteration when you try to find an augmenting path, right? And you could say that in this integer setup, the worst case is if you could find an augmenting path with value 1. And then you increase the flow by 1, and you might find an augmenting path with value 1, and then repeat it until you reach the value of the max flow. Okay, so that's the worst case. the value of the solution or the magnitude of the solution. So this f is the actual value of the maximum flow, multiplied by the complexity of the DFS or BFS search that you do for each augmenting path, so multiplied by like E plus B, let's say. Okay. Is it practical? Well, if you like consider if you take probabilities into the question, then you might say that okay, it's usually much better than this. But actually, if you consider the worst case scenario without any probabilistic argument, then actually this upper bound is kinda tight. Because, for example, you can consider my previous example. It was this. Just modify it a bit, because previously what happened, we had 20s and 10, and we had to like increase by 10 and then increase by 10 again. So an extreme version is if this is 1 and this is some C value. So then you can alternatingly find an augmenting path this way through 1, then this becomes saturated. Then find this augmenting path, which makes it unsaturated, and repeat C times. So considering the worst case scenario, this actually holds, but of course, practically speaking, it's usually better. So this is worst case. So this is worst case. Worst case this. Worst case the complexity. Okay. Okay, understand? Yeah, okay. So there are of course other algorithms. This is actually, there are problems where this particular case, when this is the value of the max flow, we have here the value of the max flow, can be actually practical. But of course, in other setups, there might be like other algorithms that are faster. So that's why it's usually useful to have multiple flow algorithms like in your library. I might talk about a few of them later, but yeah, now it's not really worth explaining one more algorithm. This is also useful because this algorithm itself can help us proving like a very important relationship, which is also often used in problems. We also proved as a side result that the value of the minimum cut equals to the value of the maximum flow, right? And actually this algorithm can help us find the minimum cut by considering the final state, okay? So yes. Okay. It's like 5 minutes left, so I guess 5 minutes is not enough for inboxes. So I guess we will just finish the class for today, okay? And we will continue with something on Friday. Yeah, Friday, because tomorrow you have some, I don't know, other program to attend. Okay, let's finish here. So thank you for your attention. Have fun at the contest, enjoy your meal and so on. See you.